I know. Why isn't the projector on? Oh, because it's muted. There. Okay. Suzuki coupling. So the whole idea of Suzuki coupling is this. And I won't even put the benzene ring in. I'm going to take something that's attached to a bromide, and I'm going to couple that R group, which in our case has been a benzene ring. I'm going to couple that with the R group that's attached to the dialkyl borane. So the idea here is to couple, let's say, R1, and R2 together to make an alkane. And so the reagent I would use would be palladium and then potassium carbonate. So the palladium metal takes the boron and the halogen, it brings those two together, and then lets the R groups couple to each other. That's the big picture of what Suzuki coupling is. And that term coupling, where did we run into it before? Free radical halogenation, where one of the termination steps was to have the two R dots coupled together. So our real question is, I can have my R1 with my bromine be anything. What we've been doing is we've just been saying, let's make that a benzene ring. And then the question is, what's R2 dialkyl borane going to be? And that's where we've been taking a step back and saying, let's synthesize that first and then couple it. So there's two ways you can couple two ways to make an alkyl borane. The first is we take something like an alkene and we react it like we did last semester with the BH3. So last semester we said hydrogen, boron add cis, and they add anti-Markovnikov, which means that the boron goes to the carbon that is most or least substituted. Okay, I'll do it again, then everybody can chime in, including those that are talking. Ready? The boron's going to add to the carbon that is least. Thank you. So when I take a molecule like this cyclohexene, I know I'm going to add the boron. And now it's just a B with two OR groups instead of last semester being a B with two H's. And then the hydrogen's going to add cis, which forces the methyl group to be on the dashed wedge. So now if I take this molecule and I take my benzene ring with the bromine on it, and I now couple those two together with the palladium, carbon, and potassium carbonate, what two groups are going to couple together? The benzene ring and everything that's attached to the boron through the boron. So if I want to, I just simply say, okay, let me write my benzene ring without my BR group. And what am I going to attach to that? I'm going to attach the cyclohexane ring and that cyclohexane ring has the methyl group down because the hydrogen is up, and the stereochemistry of the boron is preserved so that if the boron was on a bold wedge, the benzene ring is now on a bold wedge. So probably the better way to look at this is to write out the molecule with the boron, erase it, and then attach to that whatever's attached to the bromine. Kevin?
Could the bromine be a chlorine?
Sure.
Okay. So
It could be any halogen.
any halogen?
Yeah, could be any halogen. And we're not worried about how did I synthesize the bromobenzene, because hopefully at this point everybody would say, well, I'd take benzene and I would add Br2 and FeBr3 to make that part of the molecule. It's the other part that comes from the boron that is a little bit more difficult. Okay. So that's the double bond.
The bridge between in the product is there anything there on that?
Let's do it this way. Okay, I just erased the boron. So what am I going to attach to it? The benzene. So it's a bold wedge. It's a bold wedge with the benzene ring now attached to it. So if it's like this and that boron's on there, take it away, put on the benzene ring. So that's what we do with the double bond. And the stereochemistry of adding the H and the boron cis is really only in play when you've got like a cyclohexene that you're starting with. You have to have a cyclic alkene in order to see the stereochemistry of the H and the Br adding cis. Now, you asked triple bond. Okay, we started with triple bonds this year, and I just kind of said, when you add BH3 to a triple bond, you do the same thing as you did with do the same thing that you did with BH3 adding to a double bond. So now if I add my H and my BOR groups to that triple bond, where is the H going to go? The more substituted, which means it's going to go to the carbon in the left, right, middle. Well, not technically. It adds to the middle. It adds to the middle carbon, right? It adds to the C triple bond C with the CH3. Sarah?
Is it, that one is the most circular because it's the longest group that's attached to the triple bond?
Yeah, well, yeah, because just having a methyl group is more sterically hindered than a hydrogen. So, but whether we say more sterically hindered or more substituted, for the most part, those are equivalent. So we're going to add the H to that carbon. Okay? And then I'm going to end up with a double bond with the carbon on this side. So what goes where? On the right-handed carbon. Vinny? What do you think? Boron. How does boron add? Anti-Markovnikov and cis. Because remember, it's a four-membered. They got to both add to the same side, so it's the opposite. So the boron adds here to the same side as this hydrogen. So both of these groups added. And now the boron adds to the least substituted or the least sterically hindered hydrogen. So now I can couple this dialkyl borate, or this one, with anything with a bromine attached to it. And so what I would do is erase the boron, erase the bromine from whatever I'm adding it to, and just draw them together. That's the coupling. And that's really all we can do. We can only react the dialkyl borane with the hydrogen to either a double bond or a triple bond. That's it. So does that help with that? Okay. What was next on the list?
Triple question, so is it the same thing if you have a double bond too?
If I had a double bond,
So instead of a triple, if you had a double bond, is it just the same thing?
that's what I did up here. That's what I did. That's what I did here. So yeah, the same thing with the double bond or triple bond. Add the hydrogen and the boron, cis, anti-Markovnikov. And if there is no Markovnikov, if they both have the same number of alkyl groups, then 50% of the time it goes to one, 50% of the time it goes to the other, and you're going to make two different products. Okay. What else? Because that would, like my time, my attention span's like 10 minutes. And we're beyond the 10 minutes when I ask you first for a question. So there was something about blocking.
Is that whole bunch? Do you think it's
I didn't, because I was trying to get the computer up and running.
It was either blocking and then it was like the naming. I forget something else. Or the aldehydes. And
Those were the first three. Okay, so let's do blocking. But in terms of blocking, I want to also review something else. So the problem I think you're supposed to do blocking with is what? You've got an O with the C double bond O with the CH3, and then over here you got a methyl group, right? That was the problem in the,
yeah.
yeah. My mind isn't so bad that I'm ready for the home yet, but people rattling stuff off to me while I'm doing something else isn't working well. So this is what we wanted to make. And then one of the other problems was something like this, where we wanted to add like an OCH2CH3, right? That was another, and there was one with an O with the tertiary butyl group.
That was the one with blocking though.
Well, I know, but I'm going to expand the blocking to do something else that I want to talk about.
The bottom one had a meta CH3 as
Up here?
well.
Okay. I might as well do the exact homework problem. That's okay. Remember, these are formative problems. They're for you to figure out what you don't know. The summatives on the exam are coming after Easter, where you will have to then do this without help.
Is the position like how?
The position
How
of
specific is the position? Like it's so for like the CH3 is supposed to be to the one over. Does it matter if it's there?
it wouldn't matter where the methyl group is, except in my order. Except in the order of reagents, because that was another question that was asked. Could I add an NO2 group, add another group, and then go back to continuing on with my diazonium salt, which I said yes. So I'll expand upon that here. Here's the issue. I'm finding that people are confusing these two different oxygen groups that they're putting on the ring. Okay? So it is how many steps to take a benzene ring and to convert it to an OH. It's like 4 steps, right? NO2 to NH2 to diazonium to OH. Okay? And those 4 steps, it's always going to take those 4 steps. So if you want to put an OH group on the ring, those are your 4 steps automatically. So you're going to have to be able to go like I just did with those reactions. Now once the OH is on the ring, you have 2 choices. Well, you have 3 choices. Leave it alone, or convert it to an ester, or convert it to an ether. Okay? Now those reactions are not the same. So remember that if we want to make an ester, right, if I want to make an ester, which we did in lab this week if you're in lab, how do I make an ester? I react what, and what? Carboxylic acid. So let me write that down. Carboxylic acid plus and I need sulfuric acid or some acid catalyst. Okay, so if I want to make an ester, I need to the alcohol, I need to add a carboxylic acid and then acid as the catalyst. And that is known as Fischer esterification. So what does that mean for this molecule? It means that if I want to make an ester out of it, I just need to add the appropriate carboxylic acid. Like we did yesterday, or like we did whenever you had lab. Okay. But there's a problem with Fischer esterification, right? Fischer esterification is what? Equilibrium. So that means we have to use an excess of one of the reagents in order to use Le Chatelier's principle to push the equilibrium to the right. And then usually we use an excess of the carboxylic acid, and then on the other side I've got my ester and my carboxylic acid, and I've got to somehow get rid of the carboxylic acid, which this week we added sodium carbonate to that. The sodium carbonate reacted with the carboxylic acid, produced CO2 from the carbonate, it fizzed, but more importantly it made the deprotonated carboxylic acid, which is water soluble. So then we extracted the carboxylic acid as a carboxylate into the aqueous layer and left the ether in the organic layer. Okay. And that's what we're going to do in experiment, whatever it is, the last one we're doing, the unknown esters. Okay. There's another way to make esters that doesn't involve the equilibrium. So maybe I want to do that, which means that I should take my alcohol and react it with a carboxylic acid chloride. And we've seen carboxylic acid chlorides before, right, in Grignards. We haven't done the mechanism of Fischer esterification yet. I mean, we'll need to for lab. But you could imagine this alcohol coming in and adding to the carbon, and then this pair of electrons going up there. And then the O minus, the molecule says what? I want to reform the double bond. So it tries to bring the electrons back down and needs a leaving group. And so what's the good leaving group? The chloride. So it kicks the chloride off and there's your ester. Okay. We've talked about that before with Grignards and H minus. That same process. Oh wait, that was also in the video for today too. Right? Because that's the difference between an acid and a derivative and an aldehyde, because when the nucleophile adds to an aldehyde or ketone, it tries to reform the double bond, but there's no leaving group, so it's stuck. But if it's an acid or an acid chloride, there's a leaving group, and so it can reform the double bond. See, part of today's video was useful. And I don't know how many times I'm gonna say that. I'm gonna say that over and over again. You add a nucleophile, if you can reform the carbonyl, that's what the molecule is gonna do. Okay? And that's not a new description of it, because we had a seminar speaker who was a student here for a summer research program like 15 years ago, and when she went over esterification, she said the same thing. What I tell my students is, if this wants to reform a double bond, I never taught her organic, but I wish I had, because then at least I know something would have stuck. Right? So it wants to reform the double bond. No equilibrium, because chloride is a really good leaving group. So then, now I can form my ester one shot, and I don't have to worry about equilibrium. I don't have to worry about excess reagents, removing. I can do this in one shot. So what am I doing here? Because you're not answering the question about blocking. No, I'm not. But what I want everybody to be able to do is, okay, let's differentiate between adding to make an ester and an ether. If you want to make the ester, you can use an acid chloride, or you can use a carboxylic acid. Now I'm going to take that one step further. Oh wait, this is a homework problem too. Because the acid chloride can also be used to make an amide. So just like an OH group will add to a carboxylic acid, chloride, and it'll make an ester, nitrogen can do the same thing to make the amide. And as a matter of fact, this is a homework question, right? And I even gave you the answer. I said the acid chloride adds to the nitrogen, not the oxygen. Why? More electronegative, we're getting on the right track. We're moving away from the right track. It's more nucleophilic. So the nitrogen is a better nucleophile. Because remember, what's that first step? That first step is to attack the carbonyl, which is essentially a nucleophilic, electrophilic species reacting. Okay? It has no SN term. It's not SN. It's the nucleophile adding to the electrophilic carbon of the carbonyl. So the stronger the nucleophile, the better it will add. Okay. And so if you do that, you're then going to add your alkyl group or your acetyl group to the nitrogen, and you're going to make that amide. And then later on, when we talk about carboxylic acid derivatives, what we find is that when you add acid to an amide, it goes back to a carboxylic acid and a nitrogen. That's called hydrolysis. That's what you did last week in your synthesis. Okay. So you can use an acid chloride with an alcohol to make an ester, or with an amide or with a nitrogen amine to make an amide. So that's how we would make this. So I'll come back to the blocking on that in a minute. Ether. Different functional group, different ways to prepare an ether. So how many ways do we know to make ethers? I seem to recall somebody's name, ether synthesis. Williamson ether synthesis. Does that help? Yeah, probably not. What was the Williamson ether synthesis? It was just an SN2 reaction to make an ether. That's all it is. So, take my alcohol and convert it to an alkoxide. How do I do that? Sodium, potassium, NH2 minus, C minus, H minus. Tons of ways to make the alkoxide. True Williamson, sodium metal. But neither here nor there. So then what am I going to do? I'm going to react that with an alkyl halide. What kind of reaction is that? SN2. Just said it a minute ago. It's SN2. What are my restrictions on the alkyl halide? Can't be tertiary. So in other words, primary or secondary, but not tertiary. Because if it's tertiary, what happens? E2. I hear lots of SN1s. E2. What other way can I make an ether? Well, what I could do is I could take two alcohols and react them together with acid. So what's going to happen here? First step. Oxygen attach hydrogen. Protonate what? Protonate the oxygen. Protonate one of the oxygens. Right? Whenever you have an oxygen with acid, what do? Protonate the oxygen. I'll have to say that more by the end of the semester so you could repeat it in unison. Okay. But I'm going to protonate the oxygen. Which one? I'm probably going to protonate the one that then's going to have water leave to form a carbocation. So it's going to depend on what the R groups are. That would be my best strategy. Have a secondary or tertiary alcohol, add the H+, have the water leave, carbocation, my other alcohol comes in and adds ether. Now what if they're both like primary? Then I protonate one of the oxygens, the primary alcohol comes in, kicks off the water in an SN2, and I make my ether that way. Right, that was a side reaction last semester at lab. So either way, I can use two alcohols and acid. Or I can use an alkoxide and a primary or secondary halide. Or you could probably make the argument that I could use a alcohol with a tertiary alkyl halide, because the tertiary alkyl halide, what's going to happen? Halogen's going to leave, carbocation, and the OH adds.
The two alcohols up here, what are you doing with them? You're adding them together?
I'm adding them together with H+. So here's three ways to make ethers.
So you can add the two alcohols together with acid if it's tertiary or secondary,
Or even primary.
but you can't add an alkoxide to a tertiary
halide because that'll undergo E2. Because the alkoxides are nucleophiles, but they're strong bases, and so they have that personality trait where the first thing they want to do is attack. And since they can't attack because it's a tertiary halide, they get miffed, and then they decide to rip a hydrogen off of that molecule to form a double bond. If you really want to give them personality, there you go.
Can you explain the last one, the alcohol with the tertiary alkyl?
So if we've got a tertiary alkyl halide, it's going to lose the halogen to form the carbocation, and then your alcohol is going to come in and add to the carbocation. So now you form this, and then you lose the H plus to get you the final product.
So in the TV tenside homework problem, you could do, you could make it OH and then.
So let's look at that one. So in the tertiary butoxide problem, what are my first 4 steps going to do? Add an OH. So I need 4 steps to give me my OH. And then what am I going to do? I don't know that I want to deprotonate this. Because if I deprotonate it and make an alkoxide, I'm going to want to add what? Tertiary chloride to put the tertiary butyl group on. That's probably going to go more E2 than it is. So my alternative here would be to use what? What did I just say? I could use another alcohol with acid, right? So I could say, oh, let's go ahead and react this with tertiary butyl alcohol with H+. The H+ would react with the tertiary butyl alcohol, form a water. The water leaves. You get a carbocation, and the phenol ring adds.
Now, could you have any halide group on that end?
And the other way to do that is to say, you know what? I'm going to take my phenol and I'm going to add it to something like a tertiary butyl chloride.
But isn't that gonna go E2?
No, it's not. The alcohol is not a strong base, right? In order for us to do E2, I need a base. So the chloride's going to leave, the phenol's going to add to the carbocation, and then we're going to make the tertiary butyl group. Kevin?
I did that for my answer, but I put AlCl3 to like take the chlorine off. Does that work or no?
I thought you were going to ask me, like, if the chlorine leaves and you get a carbocation, shouldn't that add to the benzene ring instead of adding to instead of the OH attacking it? What you do when you add AlCl3, you're deliberately making that happen. So I would stay away from aluminum trichloride, and I would take my chances that the phenol is just going to add quickly to the carbocation than to have the carbocation add to the benzene ring. So I'd take my chances that way.
What if I like put chlorine on the ring and then I added NaOH?
If you had a chlorine on the ring and added an NaOH to it, it would deprotonate the O.
Yeah,
And then once you have the O minus, you can add a primary or a secondary halide to that to make the ether.
I would get my.
Yep. Well, you can't. What you can't do is you can't react this with this because that's going to go E2. So that's why these two are better alternatives. Those are better alternatives to the Sarah?
So for the second one, for the alcohol, like the CL, is that also gonna require a proton for
Nope.
CL?
Nope. Because that's a tertiary halide. Right? We've talked all year about tertiary halides.
Yeah,
They can break the carbon-chlorine bond and make a carbocation.
okay.
So that's going to be an SN1.
Where's the other one? Is that-
Whereas the bottom one's going to be, we're trying to do SN2, but instead we're going to do E2.
Okay.
All right, so I took a roundabout way here. So are we a little bit more clear? Maybe you were perfectly clear, I don't know. But are we a little bit more clear here? We have to be careful whether we're adding an ether or an ester, because there's two different sets of reactions to make those two functional groups. So you want to make sure that you write the right one. Okay. So then blocking. It's okay. So we wanted to make this molecule by blocking. So a couple of different ways to do it. Give me your suggestions. What do you want to do first, Brian?
Alcohol,
Okay, so I want to go through my 4 steps to put my OH on the ring, and I'm going to put my OH here because that's where it's going to end up in the final product. Okay, so there's my 4 steps. If you're trying to be psychic for the next test, how many times do you think you're going to have to do those 4 steps? At least once, right?
Every single problem.
We won't go every single problem, but you're going to have to do it at least once. Okay? So if nothing else from today, if you don't know those 4 steps, you need to know them over the next 2 weeks. All right, so I put my OH on there. So what do you want to do now?
Block it.
You want to block it? So we're going to block it by adding what? SO3 and H2SO4. And what's going to go where? SO3H is going to go to the para position. That H is incredibly important. It's worth at least a point. All right, so I went to the para position. Now, why did it go to the para position? Well, because the OH is what kind of director? O and P. Going to the para position, it's kind of sterically hindered, right? So most of it's going to go to the para position because of sterics.
So you wanted to block out the ortho position, you block the ortho. Like that.
If I wanted to block out the ortho position,
Could you? You would have to use something different.
I'd probably want to use something different if I wanted to block out the ortho position. There's ways to do that.
Okay.
There are ways to do that. The one way I would think would be you could change that ortho position, or you could change the ortho position to an NH2. And then when you're done at the para position, take the NH2 to a diazonium and add that weird H2PO3 that then takes it to a hydrogen. Okay, so now what am I doing? I'm adding my methyl group, right? So I'm going to add my methyl group, which is now forced to go ortho, and my SO3H group is there. Now at this point, make the OH group into the ester, By doing what kind of reaction? Like a Fischer esterification, or using an acid chloride, and then take the SO3H group off with steam.
Could you take it off now and then give me?
Yeah, I could take it off now. I could take it off now, I could take it off later. It doesn't matter. As long as, again, with all these problems, what's the critical thing? Get all the steps right. If you have like 5 incorrect steps, you're going nowhere. Each step is a letter that makes up a word. If the letters aren't right, the word is nonsense. I thought that's a great analogy. So you just got to get them right. Reem?
I made it an ester before I added. Is that okay?
Yeah.
Okay.
And that's fine too. Actually making it an ester would, well, see, this is where we would research. On paper it works fine.
Okay.
But when we learn about esters, we're going to find that sulfuric acid and water is going to strip it back to the alcohol. So I might hold off on making the ester until the end. But see, that's a fine detail if I'm actually going to go to the lab and do this. So right now I'm a little more forgiving in terms of reactions, because as long as they're doing what they should do, then any more complicated than that would be. What our biggest problem when we go to multifunctional groups is we try and do one thing to one, but we're doing it to the other. And that's what makes synthesis so complicated. Every functional group I put on, I got to make sure that I'm not doing something to it unintentionally.
The blocking problem from the homework though is kind of like, did you do that one?
Wasn't that this one? Yeah, you wanted to convert this to this.
Yeah.
So 4 steps to get to the OH. Then you could block. Then you could add the methyl. Then you could turn that around and make the make the ester, and then on block. Kyle?
The block you
Yep.
Can you turn the alcohol into an ester before you add the methyl?
Yeah. What's the key to the direction? It's the O. It's the O. So when the O is attached to the ring, it's an orthopara director, regardless of whether it's an OH or an ester.
With the heck problems,
The heck problems.
yeah, were we supposed to like really synthesize or show the synthesis of the bromo?
You could show. Actually, for the heck problems, all I asked was take an alkene, take an alkyl halide, couple them together.
Okay,
So it's your choice. I didn't ask you to synthesize anything before that. And actually, with the Suzuki, if you just gave me the dialkyl borane and the alkyl halide, you're okay. Okay? Well, I will release. For that homework problem, there's both an answer key, there's a written answer key, and there's a narrated answer key, I believe. So I'll release that later this afternoon. I'll take your homework problems, and then you can take the take-home quiz. And then that I will collect up on Monday. And we will not have an in-class quiz on Monday. No,
Why?
because you can't fit a triple bond inside of a 5-member ring.
So how would you make that?
How would I make that? Well, that's gonna be a little rough.
Are we taking both of these?
No. I'm not taking both of those. That's somebody's letter of recommendation.
So we don't know any way to do that, or
You're fine to leave it at like that now. We'd have to really think about some creative ways of doing that. Right?
yeah. Could you do a double bond and then? Oh well, no, because you have to have a double bond.
It would be so good if that was not in the ring, the triple bond wasn't in the ring, because then that's how we would do it. So I don't know what to say. We